next speaker is Teena Gerhardt, who's going to tell us about trace methods for equivariant algebraic K-theory.
Thank you very much. Thanks to the conference organizers, and thanks also to the organizers of the semester-long program. This has been amazing to be here. I want to tell a story today about trace methods for equivariant algebraic K-theory, and the work that I'm going to talk about is joint with David Chan and Invar Klang. But before I get to this story about equivariant algebraic K-theory, I want to say a few things about just ordinary algebraic K-theory. So, what is algebraic K-theory? Well, I'm going to say in sort of a vague sense what algebraic K-theory does. So algebraic K-theory is something that we could feed a ring, or maybe we want to give it a ring spectrum. So for a ring or ring spectrum R, we can associate its algebraic K-theory, which is a spectrum K of R, which we saw already quite a bit in Ishan's talk this morning. So we can associate this spectrum to any ring. And one reason people care a lot about algebraic K-theory is because it has a lot of applications across mathematics. So K-theory has important applications to number theory, algebraic geometry, geometric topology. I'll come back to that one in a few minutes. Geometric topology. And for instance, we saw that it has applications to other areas of homotopy theory as well. So algebraic K-theory is sort of one of the themes of this conference because its relationship to the telescope conjecture. We already heard this morning about how K-theory played a central role in the disproof of the telescope conjecture. So K-theory has a lot of applications. Maybe one note is that, K-theory originated as an invariant of rings, but we can take the K-theory of a lot of other kinds of objects as well. So if we have a nice enough category, we can take its K-theory. So maybe a note that we can take the K-theory of nice categorical data. So for instance, of what's called a Waldhausen category. So this is a category with a notion of cofibration and weak equivalence. So if we have a nice enough categorical data, we can take the K-theory of that as well. So there's been a lot of interest in algebraic K-theory across many decades now because of its applications to these other areas of mathematics. But one thing about algebraic K-theory is that it's sort of known for being really difficult to compute. It's sort of hard to get our hands on what is algebraic K-theory. Even for some pretty simple rings, like the integers, the algebraic K-theory is not completely understood. Okay, so this is not necessarily an easy invariant to get our hands on. But there has been a method of approaching algebraic K-theory that's been hugely successful in recent years, which is called trace methods. So trace methods is an approach to understanding algebraic K-theory. And the idea of trace methods is simple enough. The idea is this. Well, algebraic K-theory is difficult to understand, so let's try to approximate it by things which should be more computable. So we're going to try to approximate K-theory by more computable invariants. Okay, so what was the original sort of approximation of K-theory by a more computable invariant? Well, algebraic K-theory is an invariant of rings, so I might try to approximate it with another familiar ring invariant. So in particular, there's a trace map from algebraic K-theory. So if I have R, a ring, there's a map relating the algebraic K-theory of the ring to the Hochschild homology of a ring. And this map is called the Dennis trace. So Hochschild homology is a classical invariant from homological algebra. And this is quite an old trace map relating algebraic K-theory and Hochschild homology. Now the plus minus on the Dennis trace is the following. So I'm trying to approximate K-theory by things that are more computable. The good news is that Hochschild homology is way more computable than algebraic K-theory. It lives purely in homological algebra. We could define it really explicitly with some chain complexes. So in terms of relative computability, this is very computable. The bad news is that this map loses a ton of information. And that's not unexpected, because Hochschild homology is a purely algebraic thing, whereas this, I guess I didn't say this, but when we write KQ of R, we mean the homotopy groups of this space or spectrum. So this is a topological thing that's happening on the left. We kind of expect maybe we're losing information. Okay, that's okay. So it seems like maybe what I want here, if I want to do better, is I want to have a more topological version of Hochschild homology. People laugh because it was named accordingly, right? So we do have such a thing, our good friend topological Hochschild homology. So topological Hochschild homology was first constructed by Bochstedt, and this story grew out of ideas of Waldhausen, Goodwillie, Bochstedt, and others. So what is topological Hochschild homology? I'm going to tell you actually how we can construct this, because it will be important for our story. So topological Hochschild homology now is going to take, instead of a ring, it takes a ring spectrum R, which remember just means that we have a spectrum with a way of multiplying, and we have a unit map as well in R. You can do this for actual rings by taking the Eilenberg-MacLean's ring spectrum of your ring. So this generalizes rings. So for a ring spectrum, what am I going to do? I want to define what's called the cyclic bar construction on R. And so let this be, I'll write it out, this is called the cyclic bar construction on R. And this is a simplicial spectrum. And I need to tell you what is it at each simplicial level. So what is this thing? The Q simplices of this cyclic bar construction look like R smashed with itself Q plus 1 times. So draw a picture. So we've got R, R smash R, R smash R smash R, and so on. It's supposed to be simplicial, so there's supposed to be face and degeneracy maps relating these simplicial levels. So I should have face maps in my picture going down, degeneracy maps going up. And what are those maps? So I need to define face maps. Let's say an I face map, which is going to go from Q plus 1 copies of R to Q plus 1 copies of R. And what is this thing? Well, if I really pushed you to give me some maps from 3 copies of R to 2 copies of R, probably what you would say is let's just use the multiplication and some different coordinates to come up with maps. So I can do that. I'm going to write this as we do the identity some number of times, then I would multiply 2 adjacent copies of R, and then I would do the identity however many times I need to get to the right number of copies of R. And that makes sense as long as I is less than Q. It stops making sense when I is equal to Q because there's nothing to the right of that last copy of R to multiply it with. So what do I need to do? I need to bring that last copy around front and multiply it with the first copy. So I write tau, and then I'm going to do multiplication smash a bunch of identities, where tau, let's put it over here, tau rotates the last copy to the front. Okay, so that's what I do when I is equal to Q. And those are my face maps going down. The degeneracies, nothing too magical is happening. In the degeneracies, they just insert the unit in various places. Okay, so I have face and degeneracy maps. There's actually, I claim, one other operator floating around here, which is related to this tau. So maybe I'll think about what tau does at each level. So I'm going to call it tau sub Q, and this is going to be the map from Q plus 1 copies of R to Q plus 1. Same notation, just rotates the last factor to the front. And what do I want to note about that? I want to note that that actually generates a group action at the different levels of my picture here. So this generates a cyclic group of order Q plus 1 action at level Q. So in other words, in my picture, like here, if I bring the last factor to the front, that generates a C2 action. Here it's a C3 action, and so on. The reason that I mention that is because this operator tau makes this actually something better than just a simplicial object. it makes it what we call a cyclic object. So it has a simplicial structure and also a cyclic operator, and these all satisfy some identities with respect to one another. And the reason that we like to know is that this is cyclic is that, so the cyclic bar construction, hence the name, the cyclic bar construction is not just a simplicial object, it's a cyclic object, which means by the theory of cyclic sets that when you take the geometric realization of a cyclic object, this has an action of the circle. So this thing has an S1 action on it. That will be very relevant for us in a moment. Okay, so I was trying to come up with a definition of topological Hochschild homology. If you're familiar with ordinary Hochschild homology, you might recognize that I could define ordinary Hochschild homology just like this if I changed all the smash products to tensor products and all the ring spectra to rings. That looks like the Hochschild complex. So what is THH, the topological Hochschild homology of R, is just the geometric realization of this cyclic bar construction. Okay, so this is, I claim, an approximation to algebraic K-theory. So the good news is that just as we had a Dennis trace relating algebraic K-theory to Hochschild homology, there's a Dennis trace map relating algebraic K-theory to topological Hochschild homology. And we were hoping that THH would be a better approximation to algebraic K-theory than Hochschild homology was, and it is. So that's good. And still, in the grand scheme of things, relatively computable. We have some nice computational tools for THH as well. But we can actually do yet better. So we can get a better approximation still. I'm going to avoid this board because it's hard to read from the side of the room. So we can do better in our goal of understanding algebraic K-theory. And the next approximation is what's called topological cyclic homology. And Ishan mentioned TC in the first talk. So topological cyclic homology. Topological cyclic homology was first defined by Bokshed, Shang, and Madsen in the 90s. But many people may be familiar with the fact that trace methods has seen a huge amount of progress in recent years, in part because this was revisited, the definition of topological cyclic homology, by Thomas Nicolaus and Peter Schulze in 2018, who gave sort of a different characterization of the definition of TC. The exact definition of topological cyclic homology is not super relevant for what I'm going to talk about today, so I'm not going to go into how we define TC exactly, other than to say the following. The topological cyclic homology is built from topological Hochschild homology. So it's built from THH with its S1 action. And topological Hochschild homology has something called a cyclotomic structure, which is essential for defining topological cyclic homology. So starting from THH and understanding how S1 acts on it, we can build this approximation TC. And the thing that makes trace methods go is that we have a map. So we had a map, the Dennis trace. It lifts through the topological cyclic homology of R. And this map is called the cyclotomic trace. The cyclotomic trace was first constructed by Bokshed, Shang, and Madsen. And the thing that makes it go, that makes trace methods so successful, is that TC is a good approximation to algebraic K-theory. So that is, of course, very vague. There are a lot of very explicit theorems to that effect due to a number of different authors. The sort of classical one is Dundas, Goodwillie, McCarthy, who give a precise statement about how these two are related in many cases. But there are also theorems of Household-Madsen, Housen, Matthew Morrow, and many others, talking about this relationship between K-theory and topological cyclic homology. But the takeaway from this is that this trace method approach has been hugely successful in understanding algebraic K-theory across many decades now. So a lot of the recent progress in K-theory calculations understanding K-theory comes from studying topological cyclic homology and how these are related. And so we see that, for instance, in the disproof of the telescope conjecture, that trace methods is the approach that's used to understand algebraic K-theory in producing those counterexamples. Okay, so we have algebraic K-theory, and we have this trace methods approach. What I want to tell you a little bit about today is an equivariant version of this story. So I want to tell you a little bit about equivariant algebraic K-theory. So equivariant algebraic K-theory. So this conference is part of a semester-long program on equivariant stable homotopy theory. So perhaps I don't have to sell y'all too hard on the idea that it's natural to consider to what extent K-theory can capture and analyze equivariant structures. So one might ask, is there an equivariant form of algebraic K-theory that takes an equivariant input? And a number of people have laid the foundations in this field. So, for instance, the foundational work is due to Mona Merling, also Clark Barwick, also Barwick, Glassman, Shaw, and also Malkevich, Merling. And I am going to do their work a little bit of an injustice by summarizing like a lot of really beautiful work into one really small diagram. But how should we think about what these people have done? So one way to think about what this work does is it does the following. It asks, okay, what if my input was not a ring, but a ring with a group action, a G ring? Or maybe it's a G ring spectrum. Ring spectrum. Or maybe it's a G Waldhausen category. So I take the kinds of inputs that I'm used to for ordinary algebraic K-theory, and I ask about equivariant versions of those inputs. And what do these folks do? They construct equivariant algebraic K-theory, which takes these types of things as inputs and spits out for us a genuine G spectrum. Genuine G spectrum. Okay, so I'm not going to talk explicitly about any of their constructions. Instead, I'm going to introduce it by way of examples. I think that will be a little bit friendlier. So for example, let's look at what happens in a few cases. So for example, let's say that we have R a G ring and H a subgroup of G. Then Merling proves, in her work on equivariant algebraic K-theory, Merling proves that if the order of the subgroup, so if the order of H is invertible in R, then what happens? Then if we take the G equivariant algebraic K-theory of R, and we take its H fixed points, what we get is the ordinary algebraic K-theory of a twisted group ring on R. So this is like a group ring, but it has a twist in the multiplication by the group action. So this is a twisted group ring. So this relates equivariant algebraic K-theory to classical algebraic K-theory. Similarly, if we have, if E over F is a Galois extension, Galois extension with Galois group G, Galois group G, then we could ask, like, if we take the G equivariant algebraic K-theory of E and then we take the G fixed points of that, what do we recover? And what Merling shows is that we recover there the ordinary algebraic K-theory of the field F. And there's more to this story, like understanding the equivariant version now gives you some tools to think about the ordinary algebraic K-theory of the fields and sort of operators on them. So there's a lot more to that story as well. So these are some examples of how it relates to ordinary algebraic K-theory. One of the things that we liked about ordinary algebraic K-theory is that it had applications to these, I claimed at least, it had applications to these other areas of mathematics, like number theory and geometric topology. And so you could ask, do we see this kind of thing in the equivariant setting as well? And we do. So for instance, it has applications to number theory. And I'm not going to talk about that, but there's work of Eldon Almanto and Ningxuan Zhang talking about applications of equivariant algebraic K-theory to number theory. But part of the original motivation for studying this, at least for Malkiewicz and Merling, were applications to geometric topology. So let me say a word about that. So applications to geometric topology. So first let me tell you a little bit about what happens classically. So classically, I said that the input to algebraic K-theory classically was a ring or a ring spectrum or one of these maybe Waldhausen categories. So what was Waldhausen doing when Waldhausen developed the notion of Waldhausen categories? He was thinking about the algebraic K-theory of spaces. So that categorical input is a way of extending algebraic K-theory to study spaces. So for a space X, in the classical setting, Waldhausen defined A of X, which is just notation for the algebraic K-theory of X. The algebraic K-theory of X. And the motivation here is that in low dimensions, for instance, for K0 and K1, there are some very classical applications of K-theory to geometric topology. And Waldhausen's A of X allows us to extend those to sort of higher dimensions. So there's a lot of work here, and all I'm going to say is, again, something very vague, which is just that A of X is somehow related to the study of automorphisms of manifolds. And so, for instance, one sort of theorem in that body of work is the parametrized H-cobordism theorem. So when we work in the equivariant setting, we could ask, can we do this kind of thing equivariantly? Like, for a space with a group action, is there some notion of algebraic K-theory, and will that be related to some notion of automorphisms of manifolds equivariantly? And Malkiewicz and Merling have studied that question quite a bit, and they do the following. So Malkiewicz and Merling define a G of X for a G space X. So this is genuine equivariant A theory. And they have a large body of work, a big program where they're working on an equivariant version of the parametrized H-cobordism theorem. So they argue that this is the right object to be in the framework for equivariant parametrized H-cobordism. H-cobordism, and this is a big, there's work in progress. This program isn't done. There's a lot of work out there, but this is joint work of Malkiewicz and Merling, also with Goodwillie and Igusa. So this is sort of in progress. Okay, that's all to say that equivariant algebraic K-theory, it has applications just like ordinary algebraic K-theory does, as well as relationships to ordinary algebraic K-theory. And so there's a lot of interest in trying to compute equivariant algebraic K-theory. But one limitation is that currently there aren't a lot of computational tools for equivariant algebraic K-theory. So there are some calculations that exist, some explicit calculations. For instance, in this work of Almanto and Zhang, they do some explicit calculations of equivariant algebraic K-theory. There's also work of David Chan and Chase Vogeley, where they use different tools to do some explicit calculations. But in general, there's no real general approach to understanding equivariant algebraic K-theory. And so if you put together everything that I've said so far, it seems like there's a natural question there, which is that classically, this trace methods approach has been so successful in understanding ordinary algebraic K-theory. can we do trace methods in the equivariant setting? So the question I want to talk about today is, can we develop, I don't know how to make this question, can we develop trace methods for equivariant algebraic K-theory? Okay, so let's say that we're trying to do this. We're trying to think about trace methods for equivariant algebraic K-theory. And what is the first thing that you would want? Well, in the classical setting, it seemed like that Dennis trace, that map to THH, that was the start of it all. So I think I want that. But what should the right-hand side be? Now I need a version of THH that's going to take one of these equivariant inputs, right? If I'm going to compare it to equivariant algebraic K-theory. So I want THH, but I want THH that takes an equivariant input. And so at first I might feel like, well, I'm in luck because a lot of things like that seem to exist. There are a lot of generalizations of THH out there that take equivariant inputs. So for instance, I might think about the following options. So here are some options. There's what's called real topological Hochschild homology. So real topological Hochschild homology, or THR. So this is THR. This is due to Hesselholt and Madsen, also Emanuele Dado, and it's well known because it's an approximation for real algebraic K-theory. So this is an important thing that we study. And it takes as input a ring or ring spectrum with anti-involution, which is a kind of C2 ring spectrum. So this one takes an equivariant input, so maybe that will be useful. There's CN twisted THH. So that one is written THH CN. That's due to Engelbeit, Blumberg, myself, Mike Hill, Tyler Lawson, and Mike Mandel. I'm going to come back to this one in a minute. This takes as input a CN equivariant ring spectrum. And there's actually a whole new family in very recent work of Gabe Angelini-Knoll, Mona Merling, and Maximilian Peru. There's a whole new family of generalizations of THH, and I'm going to mention one thing in their family, which is a quaternionic version of THH, which they write as THQ, which takes as input twisted C4 equivariant rings. So we have these options, but you can possibly see kind of immediately, like none of them seem totally like the right thing because my equivariant algebraic K-theory, sorry, G's finite. Maybe that's like always implicit, but anyway, G's is supposed to take any finite, equivariant for any finite group, and these feel somewhat restricted in what kinds of groups they take input for. But you could ask the question, like, what if I restrict to one of those cases? Like, let's think about G equals Cn for a moment and see if I can say anything. So if I only think about the cyclic group of order n, so we thought about this in some work a few years back. This is work of Catherine Adamic, myself, Catherine Hess, Inbar Klang, and Hannah Giacong. We thought about the question of how is equivariant algebraic K-theory related to this twisted THH. And what we found is that if we have a CN ring spectrum R, so for a CN ring spectrum R, what we found is that there is a non-equivariant trace, non-equivariant Dennis trace that goes from the CN equivariant algebraic K-theory of R and then the CN fixed points of that to twisted THH of R. Okay, so this is nice in some ways. I mean, this is a relationship between equivariant algebraic K-theory and one of these equivariant forms of topological Hochschild homology, but it's a little bit unsatisfying in that I really would A, like to have an equivariant map relating these things, and B, I would rather not have taken fixed points on the left. So what would I like to do? Well, I would like to lift this So I'd be happier if we could lift this to an equivariant map, not on fixed points. But then we're sort of back to the drawing board because that says that this is not the correct right-hand side for that map. This isn't the correct equivariant version of THH. And I kind of already knew that because this thing, we'll talk about the definition in a minute, this thing really does take a CN equivariant input. It doesn't take a general G equivariant input, which I want my...
But the output is just a spectrum, right?
Oh, of this thing?
Yes.
Yeah, this is confusing. No, the output's actually an S1 equivariant spectrum, but in this map, I'm thinking about it just as a spectrum. So this is a map on spectra, but actually this thing is an S1 equivariant spectrum. I'm going to talk about that in a second. Yeah.
So in all of these cases, what kind of input can you give? Can you like plug in a G category, like, or can you?
Here?
Yeah.
So this thing, THR, takes a ring spectrum with anti-involution, or you can make that more categorical and define some categorical notion with anti-involution. This thing originally was defined just for CN ring spectra, and the stuff that we do, we extend that and think about spectral categories, so you can give it sort of spectral category input. This thing, Gabe is here. I'm gonna go with a C4 twisted equivariant ring spectrum. What is the most general input that you guys give this thing?
Yeah, we don't have a categorical one in the paper yet.
Okay, no categorical one in the paper yet. Yeah, so these can take sort of more categorical data. This one, not yet. So, yeah, good question.
More question.
Yeah.
So when you write kg of r, that's a spectrum with a g action, right?
Good question. It's a genuine G spectrum. So.
Anyway, oh, you've written that, and it kind of confused me.
Oh yeah. So in equivariant homotopy theory, there are these like different notions of how equivariant you want your stuff to be. A naive notion of equivariance is to ask for everything to just have a G action on it. Genuine is more genuine than, I don't know. Mike Hill always says he doesn't like the value judgment implicit in the word genuine, which fair enough. So what genuine means is that your ring spectrum is actually, instead of like, if a spectrum, originally when we first learned spectra, it's like a sequence of spaces indexed by, natural numbers or integers. G spectrum is now indexed by representations living in some universe that you specify. So I have a space for every finite dimensional representation of my group, say, and they have to be related via equivariant suspension maps.
So the G ring, is that a genuine?
That's just a ring with a G action.
Right. And
Yes.
then K of R with no G, does G act on that in some naive sense?
Oh yeah, excellent question. So yeah, I mean, K theory, is functorial, right? So the group action on your ring gives you a group action on, just like if you hit everything with just K theory, it's going to give you a group action on everything. And Merling has some interesting. Anyway, Merling's paper is really great. But as she found out when she was constructing these things, that naive version is really badly behaved in the sense that if I have two G equivariant rings and a G equivariant map between them, the map that it induces on that naive version of equivariant algebraic K theory is not equivariant, which is like not a thing that you would want to happen. And so her construction remedies that. And so this is not just the naive thing of like, take your thing with a G action, hit everything with K theory, and then like, see, you have to do something more sophisticated than that.
And that's kg of r.
Yes, exactly. Okay, so we have a trace map. This is good, but it's not quite the thing that I want. I want to upgrade the right-hand side, and I have to figure out, I just don't know what to put there. So we have to figure out what should go on the right-hand side. And I claim that we can figure out what should go on the right-hand side if we take a little detour. So we're going to take a short detour to talk a little bit about equivariant norms. And I claim that this is going to tie pretty quickly back into figuring out what the right-hand side should be. Okay, so what do I want to say about equivariant norms? Hill, Hopkins, and Ravenel, in their seminal work on the Curvaire invariant one problem, of the things that they did was they developed a lot of foundational tools in equivariant stable homotopy theory as part of their end goal of studying the covariant one problem. And so one thing in particular is they defined these multiplicative norm functors. So they defined multiplicative norms, building off of work of Greenlease and May. So they defined multiplicative norms, which are functors that take as input an H spectrum and spit out a G spectrum. Okay, and they needed these norms for H, a subgroup of G, a finite group. Okay, they needed these norms for their work on covariant variant 1, but we've seen in the years since that work, these norms have a lot of applications in a lot of different areas. They also have some nice properties. So it's going to be important for us, a couple properties of these norms. So let me mention a few things about these norm functors. One is that we might want to know how the norms interact with taking fixed points. And so in particular, we're going to think about what are called geometric fixed points, which is just one of the notions of fixed points we use in equivariant homotopy theory. So I could ask, if I take the norm from H to G of some H equivariant input, I norm it up to G, now it's a G equivariant, and I could take the G fixed points of this thing, and Hill, Hopkins, and Ravenel show that what we get is we get the H geometric fixed points of X. Okay, so we have this nice relationship between the norm and geometric fixed points. Maybe I want to know something more general though, like maybe I want to norm from H to G, but then I want to take the fixed points with respect to some other normal subgroup. So K, normal, and G. I want to take the K fixed points of that thing. So I could ask, do I understand what happens then? And it turns out there's a formula for that as well. So it's the H intersect K geometric fixed points of X, and then I norm that from HK mod K to G mod K. Okay, so this is just a more general formulation of the Hill-Hopkins-Ravenel relationship. Okay, I'm going to put a pin in that. We're going to leave that there. We'll need that momentarily. And another proposition that Hill, Hopkins, and Ravenel prove about the norm that I want to mention is the norm, if we restrict ourselves to look at commutative things, the norm is characterized by the following fact, that in the commutative case, so in particular, if I think of my norm as going from commutative H ring spectra to commutative G ring spectra, Hill, Hopkins, and Ravenel show that the norm is left adjoint to restriction, where you just think of your G equivariant thing as an H equivariant thing instead. Okay, so this is well, not really definition, but something at least about the Hill-Hopkins-Ravenel norm. So I mentioned here when I said what they did that they defined these for finite groups. That was what they needed for the covariant variant problem, is they only needed a notion of this equivariant norm in the finite case. But it's natural to ask, like, could you study these kinds of equivariant norms for other compact Lie groups instead of just restricting yourself to finite groups? And we considered that question in work of Wiegleich Engeltveit, Andrew Blumberg, myself, Mike Hill, Tyler Lawson, and Mike Mandel. I promise I'll only write that all at once. And there was related work around the same time of Martin Stolz. And what did we do in this work? Well, we constructed norms to S1. So we constructed norms to the circle, extending Hill-Hopkins-Ravenel's notion of an equivariant norm. And in particular, what did we show? We showed that if you take the norm from the trivial group to S1 of some ring spectrum R, at what is this thing, we showed that a model for the norm is given by the cyclic bar construction on R. Just to be honest, I'm going to put what's called a change of universe here. If you don't know what that means, just ignore. That's to make it like the right amount of genuineness in the equivariant setting. So what does this mean? So we showed that the cyclic bar construction is a model for the norm. You might ask, like, what is the content of that? Well, for instance, you want to prove a proposition like this to justify that it deserves to be called a norm, that in the commutative setting it's left adjoint to restriction. So we do that. But what this means is well, I mean, this looks familiar, right? That was just the definition of topological Hochschild homology. So it means that topological Hochschild homology can be thought of as an equivariant norm. It's the norm from the trivial group to S1 of R. Okay, so you could ask then, the norm from the trivial group to S1 of R is THH, which is something that we've cared about for a long time. And so you could ask, like, what about, can I take norms from other subgroups of S1 up to S1? And what would those things be? And so in this same collaboration, we make the following definition. We say, okay, well, we could define a notion of twisted topological Hochschild homology for R, a Cn ring spectrum. And what is this thing going to be? Well, this thing is going to be the norm from Cn to S1 of R.
Is this a commutative ring spectrum or just a ring spectrum?
Just a ring spectrum. It doesn't have to be commutative here.
You're not defining norms for general spectra. It has to be a ring spectrum.
Oh yeah, good point. Yeah, maybe it's gone now. So oh no, it's here. Okay, what Neil's pointing out is that, like, for Hill-Hopkins-Ravenel, this thing just took an H spectrum. But for this to make sense here, this is really taking an associative ring spectrum. So yes, these norms have a more restricted input in that sense. Doesn't make sense otherwise. Yeah, Hari.
Is the norm from E to G, where G is a finite group, like a subgroup of S1, is that just the low-day construction of, like, R tensor that? Like you said that the norm from E to S1 is the THH, and the THH is S1 tensor your ring.
Right. Yeah.
So is it true that you take the norm from E to something else, where that something else is a subgroup of S1?
I don't know. Let me get back to you on that. I haven't thought about how the low-day construction versions relate to the norm versions for the finite groups.
I think that only makes sense in the commutative case.
Yeah, that probably, right. Yes, the tensor thing only makes sense in the commutative case even here as well. So, right, yeah.
But if it's given by Bergstedt's smash product, the 1986 smash power of Bergstedt.
Okay, so we have, right, so what does this mean when I take this norm? So we give an explicit construction of this. So we give an explicit construction of this equivariant norm. And what is it? So this thing is a twisted cyclic bar construction. Cyclic bar construction. And I'm just going to tell you really roughly what it is. So I'll draw a picture. This is again going to be a simplicial spectrum, and the picture looks on the surface the same. I'm going to take the same picture I had for the cyclic bar construction. What's different is the last face map here. So the last face map. Remember, that was the one that was already a little weird. That was the one that, like, brought it around the front and then multiplied. Now it's going to pick up a twist by the group action. So it's going to come around the front, it's going to be acted on by the group, and then you're going to multiply. So the last face map picks up a twist by the group action. Now, if you really think about that hard, for ordinary THH, it was really important that what you got was cyclic. That's how we got the S1 action, right? This thing's not cyclic anymore, but that's okay because Bokstedt, Chang, Madsen have a notion of lambda n op objects. So it's not cyclic, but the geometric realization of it does still have an S1 action. So we understand what kind of structure this thing has, which is how we get something S1. Okay, so that's to say that Cn twisted THH is also a norm. So this is the norm from Cn to S1 of R. There's work of Gabe Angelini Knoll, myself, and Mike Hill, where we think, oh, what about THR? Could we think about that as a norm? Turns out you can think about THR as a norm from C2 to O2 of your input. And for THQ, their current construction of THQ is not a genuine spectrum. It's a more naive notion of equivariance, and so it doesn't quite make sense to ask if it's a norm yet, but conjecturally this should be a norm. So this should be a norm from C4 to pin 2 of the input. So all of these Hochschild constructions, there's a way to think of it as this perspective from equivariant norms. Okay, but what was I trying to do? I was trying to construct trace methods for equivariant algebraic K-theory. So before I can tell you how this all fits together, I need one more piece of information, which is that this was all a little bit ad hoc, right? Like I constructed the, lost my eraser. I constructed the twisted THH as a twisted cyclic bar construction. Like I gave an explicit construction of that norm. We do the same thing for THR. That's a dihedral bar construction. We show that that's a model for the norm. But you could ask, like more generally, can you construct norms for compact Lie groups? And there's work of Blumberg, Hill, and Mandel. And so this is sort of work in progress or a program in progress of Blumberg, Hill, and Mandel. But what do? They propose a general construction of norms for compact Lie groups. So they propose a general construction of norms for compact Lie groups. And they have a paper about this on the archive, and they conjecture in this work, so that they conjecture that under appropriate hypotheses, so I'm not going to give the technical appropriate hypotheses, I'm not going to give their technical conjecture, but their conjecture is that if you put the right hypotheses on it, these formulas for how the norm and the fixed point interact should still hold for compact Lie groups, not just finite groups. So they conjecture that if we make enough hypotheses, then the norm fixed point formulas should hold. Okay, their conjecture is actually much more specific than that, but that's roughly what it says. Okay, and I claim that knowledge, together with our, it's gone sadly, our non-equivariant trace map leads us to an idea of what the right-hand side really should have been. So, in the joint work with David Chan, myself, and Inbar Klang, we define a new equivariant version of topological Hochschild homology. So we define for G a finite group, for G finite, and R a G ring spectrum. We define what we call ETHH for equivariant THH of R. And what do we define this thing to be? We define it to be an equivariant norm. It's the norm from G to G cross S1 of R. Now that only is sensible if we give you a construction of what that norm should be. And so the construction of this norm is that this is the cyclic bar construction on R, now in G spectra, and then we have one of these change of universe functors happening here to get us to a genuine G cross S1 spectrum. Okay, so how do we justify that this is actually a construction of an equivariant norm? So as I mentioned earlier, in the commutative case, the norms are characterized by this adjointness property of being left adjoint to the forgetful functor, to restriction. And so we prove that here as well. So in the commutative case, this is left adjoint to restriction. That's a check that this actually is a characterization of an equivariant norm. And I claim that this relates to our non-equivariant trace map to twisted THH. So let me tell you how that goes. So let's let delta Cn inside. So I'm going to look at the case where G is Cn for a second. And let's think about delta Cn inside Cn cross S1. So I'm going to let this be the diagonal subgroup isomorphic to Cn. And then from the Blumberg-Hill-Mandel conjecture, so from the Blumberg-Hill-Mandel conjecture, you would expect the following. So let's say that we take ETHH, so here it's going to be norm from Cn to Cn cross S1 of R, and I'm going to take the delta Cn fixed points. So, oh, it's covered, that's sad. Here, let's put it up. Oh no, it's gone. Okay, well, really tried hard not to do that, and then I did it anyway. So I had, sadly, up there, a nice formula about how norms and geometric fixed points interact. And if you still had it, and you traced through it, you would see that if I take this norm and these geometric fixed points, what I would expect to get on this side is the norm from Cn to S1 of R. So what does it mean? It means that we expect that the delta Cn geometric fixed points of ETHH should be twisted THH. That's what Blumberg-Hill-Mandel's conjecture would tell us. And indeed, we prove that that's the case. So we prove that, so for R, a Cn ring spectrum, we prove that there's an isomorphism of Cn spectra between the Cn geometric fixed points of ETHH of R and twisted THH of R. Okay. Classically, there are other things about THH that are important to developing trace methods, like THH is Morita invariant, THH satisfies additivity. Those are two big ones that come up in the construction of trace maps in from algebraic K-theory. We prove those things here as well for ETHH, that it has those desirable properties that we're going to need to construct a trace map. Okay, so before I can tell you our main theorem, I want to say one other thing, which is that I've considered here ETHH as a genuine G cross S1 spectrum. So this is how we have constructed it. So ETHH is a genuine G cross S1 spectrum. I'd also like to have a version, so we also need a version that is a spectrum with G cross S1 action. And by that, I mean here, for people who think about these things, I mean in the sense that it's indexed by R infinity. I'm going to call that little ETHH, or like a little bit less equivariant than capital ETHH. We also need a version like this, little ETHH. And so what were we trying to do? We're trying to develop trace methods for equivariant algebraic K-theory, and what do we prove? So our theorem, oops, that's not right, Chan, Gerhardt, and Klang. Our theorem is that if we have R, a G ring spectrum, we prove that there is an equivariant Dennis trace map. There is an equivariant Dennis trace in the homotopy category of spectra with G action. And what is my equivariant Dennis trace? My equivariant Dennis trace is going to be a map from the equivariant algebraic K-theory of R to little ETHH of R. Here, I really want to think about, for this trace map, I want to think about this as a spectrum with G action and not a genuine G spectrum. And so to denote that, I can put in a change of universe functor just to remind myself that I'm thinking about this thing as a spectrum with G action. And so we construct an equivariant Dennis trace relating equivariant algebraic K-theory to a form of topological Hochschild homology. And I want to tell you a couple things about this trace map. One is, one thing that you would like to be true is that you can recover the classical, this recovers the classical Dennis trace, so that's true. So if G is E, the trivial group, this gives the classical Dennis trace. So it really is an equivariant refinement of the classical Dennis trace map from algebraic K-theory to THH. Another thing that we wanted was I wanted to lift that trace map that we had on fixed points, that non-equivariant map. I was trying to lift it to an equivariant trace map, and this does that. So this lifts the earlier trace map in the sense that I can recover that map from this one, earlier trace map. And maybe just a note about how this thing is constructed or the generality in which we do this, that I've stated it here for the RG ring spectrum version of this, but we actually construct this more generally for what are called G spectral Waldhausen categories. So we really have a more general trace map, or generally for G spectral Waldhausen categories. So part of this work is in developing the theory of G spectral Waldhausen categories, for instance, like what is the natural input to construct the trace map here, and we do that as well. So you might want, maybe as a, oh, I have 2 minutes, okay. You might want something more genuine than this, and so just a note that we also get maps from the equivariant algebraic K-theory of R to ETHH of R, the capital one, the more genuine one, on fixed points. So for all H and G. But interestingly, it doesn't in general lift to a map of G spectra. So we have maps on fixed points for all subgroups, but not a map of genuine G spectra like this. And maybe I'll close with, let me say one thing, which is that a natural question to ask is like we have this trace to THH. So from what I said earlier, the natural next question is like, what about topological cyclic homology? Like, is this cyclotomic? Does it lift to ETC? And I have a graduate student who has work in progress on that, Mark Gottlieboim, has work in progress on ETC and cyclotomic structures for ETHH. And maybe I'll close with one application, which is that this equivariant trace map. So we show that the equivariant trace gives us trace maps from the equivariant A theory of Merling and Malkovich. So we get trace maps, for instance, for X, the G space. We get trace maps from the H fixed points of their genuine G equivariant A theory. We get trace maps from that to the loop space fixed points of X. So we get, so our equivariant Dennis trace gives us traces like this for the equivariant equivariant A theory. The countdown clock is really intimidating. The equivariant A theory that Malkovich and Merling are studying as part of parameterized H cobordism. Okay, this clock is scaring me, so I'm going to stop.
Questions for our speaker?
Yeah.
Oh, this norm map, is it something like an induced representation in a multiplicative sense. I mean, it's a
Yeah, it is. We
adjoint
are supposed to
to-
think of it as something like multiplicative tensor reduction.
Right, it's just something, can you literally construct it as a tensor product indexed by cosets of H and G?
Right, it's like an index, roughly speaking, it is like an index smash product indexed by cosets. Yep. And then you sort of have to make that homotopical is what Hill-Hopkins and Ravenel do, but yeah. But yes, that is the idea of what's happening. Yeah, Neil.
So, I mean, if you could construct these things on fixed points in a sufficiently compatible way, then you'd have a morphism of spectral
Oh, that sounds so nice, right? True, but we give an explicit counterexample in our, so it's not just that we can't promote it to a map of G spectra, we know that it cannot always be promoted to a map of G spectra because we give an explicit counterexample in our paper of like it's like we do it in the level of algebra, so it's like you have a coefficient system for which there is no Mackey functor that has that coefficient system, and so so we know in general. I'm not claiming that it's not. We don't know that it's impossible to have a map like this. What we know is that our map cannot be promoted in the way that you would expect. Like you would expect, hopefully from our map, like the natural thing to try to get from little ETHH to big ETHH is just a changing universe. So you'd like to just like hit both sides with a changing universe, which we thought was kind of, Inbar's laughing, which we thought we could do. But there you get an issue over here with you have a changing universe, a cofibrant replacement, another changing universe. It's related to equivariant algebraic K-theory, but the map goes the wrong way. And in general, we can show that it doesn't split in some general sense. So the claim is not that there couldn't be a map like this, although we expect that that is the case for various reasons, that you shouldn't expect a map like that. But you definitely can't promote our map to a map like that in the way that you would want to. We tried. Yeah, John.
So there are sort of two non-equivariant models you could think of what you should mean by the H fixed points, or let's say G fixed points of G equivariant A of X, where you'll be talking about refractive spaces over X, refractive G spaces. I mean, so X is a fixed G space, I'm talking about refractive spaces over X, and then there are two categories of cofibrations you could think about. Either you ask for G maps that are G homotopy equivalences, or G maps whose underlying map is a homotopy equivalence.
Yeah.
Which of those is it that you're constructing as getting as the G fixed points? I mean, the first one, where you're taking genuine G homotopy equivalences maps to the more lax one. And you could imagine having a trace from the first that would not factor through the second.
You're asking about like what Wellhausen category Malkovich and Merling are using in their construction here?
In practice, yes.
The second one, yes?
So let's see. So we have the trace from the more coarse one.
Yeah.
And then because there's a map from the more genuine one to the more coarse one, we also get a map from the more genuine one to.
But that distinction is not the distinction between coarse and the genuine one, right?
I think that's.
Oh, okay. Okay, yeah, sure. So we're actually, I didn't want to also talk about coarse K-theory, but as Inbar just said, like our map, the thing that we're working with more naturally relates to their coarse K-theory, and then we're using the fact that there's always a map from their genuine A-theory to their coarse A-theory to get this map. But our map more naturally is a map out of coarse A-theory.
Thank you.
Could you say more about this THQ, like THQ as a norm?
Yeah, I can say a little bit. So what the question was about THQ. So this, as I said, was, maybe I didn't write, but I said is work of Gabe Angelini, Nolan, Mona Merling, and Maximilian Frew. And what they do in this work is they think about analogs of topological Hochschild homology that come from different cross-simplicial groups. And so like ordinary THH and THR are both examples of like forms of THH that are coming from studying cross-simplicial groups. That you can study other cross-simplicial groups, and this gives a bunch of generalizations, one of which is THQ. So this thing takes as input not just any C4 thing, but what's called a twisted C4 ring. I don't know. I mean, I can direct you to Gabe, who's here, who can tell you in great detail about what they've done. But this is just one of their, they develop a whole family of generalizations of topological Hochschild homology for different cross-simplicial groups. I just picked out one that I think is particularly interesting. But as I said, their current construction constructs this as like a spectrum with pin2 action. And to get a norm characterization, you really need it to be a genuine pin2 equivariant spectrum. So that's kind of work in progress. I think to establish that that is a model for the norm, but it certainly should be a model for that equivariant norm. But I direct you to Gabe.
Maybe just one concrete thing you can say is in the cyclic bar construction, you have these CNs acting level-wise. Here you would have these generalized quaternionic groups acting. So that gives you the interaction.
Yeah.
Alrighty. Oh, yeah.
I just wanted to check, so the input for ETHH is an E1 algebraic G spectrum.
Yeah, it's just a G ring spectrum.
Okay.
Yeah, doesn't have to be commutative or anything.
Yeah.
Yeah.
And can you, like, does it get more structure if you input something more structured? Like, can you quantify this? Like, what happens if I input like a normed G ring spectrum?
Oh, I haven't thought about what happens if you, I mean, you know, we know like things about what happens in the commutative case, you know, like a little, like the things like characterizing things as tensors and stuff like this that hold in the commutative case, but beyond the distinction between what happens in the commutative case and just in the associative case, I haven't thought about like what happens for other sorts of structured inputs. I mean, we know, we know various things that are true in the THH setting, some of which like, you know, there's a nice story in THH of like what happens if you take THH of a Tom spectrum or something, so you can ask like that kind of question here. We know things about that as well, but to your exact question, not really, I don't know.
All right, yeah, well, let's thank our speaker again.